Okay, worksheet 28, distance traveled. Are there two L's in traveled? I think so. Oh well. Yeah, Google says yes. Okay, fine. All right, so here's what we're going to do. We're going to use the first example with a table, and then this can also be done using graphics or using a formula and so forth. So this right here could be in like miles per hour. This could be miles, but it could be any unit as long as they're consistent. Okay, so I'm not going to worry about the units, but the units should be consistent. Okay, so what I want to do is ask a very basic question, which is how far did the object travel over the given time period under consideration, which right now let's do the entire table. So you're going to have an exercise like this on your worksheet, and first we're going to do an overestimate. So how we're going to overestimate this, and notice in your worksheet these time steps are not all equal, so you have to be aware of that. But in this example, all my time steps are equal, and I'm going to first look from t is equal to 0 to 5. I'm going to estimate that between time is equal to 0 and 5, the maximum it could have traveled, maybe it was going 5 miles an hour and then instantly went 6 miles an hour. And so I'm going to make this guess that the most it could have been going during that interval was 6 miles per hour for 5 hours. Okay, so over that interval, I'm going to take the maximum of these two, and the difference of these two items, and it's going to be 30. Okay, and so the way I'm going to indicate this for myself, just to make things easy, is I'm going to make a little box underneath here to indicate that I'm going to consider that time interval. And what I want to emphasize here is that even though we often take these boxes and like align them with either the first time step or the second bit of the time, the first part of the interval or the second part of the interval, in reality these are essentially derivatives, and they belong between the other two values. They really are offset. They're actually staggered, and so you should think of that you are finding accumulated distance or derivatives or whatever. You're going to find them over a time interval. So that's why I'm intentionally writing them staggered. So in this case it's accumulated change. So here I'm going to say 30 because the difference between these two is 5, and this is the maximum. Okay? All right, so here's what I want you to do is pause the video and try to fill in the rest of the boxes and then come back and see if you agree with me. Okay, so if you were always estimating based on the right-hand endpoint, you would have said that this was 100, for example. And the problem with that is, and you would probably said this is negative 25. So if you had fallen into that trap, it's because you forgot that we were trying to overestimate. And so in this case, make sure you overestimate. You take the maximum of the two options. Now, what is the next step? So you tell me, what do you do from here? These were all the estimates over the increments. How do you estimate the accumulated distance? Figure that out, pause the video, and then try it. Okay, so the answer I got was 230. Hopefully that's right. So what happened is I just added all those and got that answer. So what about if we save this off and say, okay, but what about if we want to under approximate? So this here was our over approximation. How do you under approximate? So do the same thing for under approximation. Here are the things that here are the individual time intervals I calculated for under approximating, and I'm going to add them all up together. Okay, so I get 230 for over approx and 155 for under approx. Okay, that's what I get. Hopefully you get the same thing. If there's a mistake, it could be me. So let's figure that out. If my video is wrong, then just let me know. So here's the thing though, if I don't tell you which way to go, I say estimate, a lower estimate, that's fine. What if you want an average estimate? So if you need an average estimate, what you're going to do is do some kind of over and under and then average the two So if you want more of an average, you can just go halfway between these two. Okay, and so what it looks like to me, it looks like 385 over 2, which is 192.5. So if you're being asked to get an average, not asked to over or underestimate, then you're going to just sort of average that. Now, the other question you may be asked is it possible that your estimate, that your overestimate or your underestimate isn't really that accurate? And that's totally possible, because what this doesn't tell you is whether or not, say, you know, maybe at time equals 3, something weird happened. Like, so I can't drag those numbers, but it's possible there's a whole bunch of stuff going on in here that you don't know in between those time steps. But the understanding is, when you're given a table of data like this, that the thing is changing slowly enough that you have to pick your time step so that your numerics work out. So it's possible that you messed that up, but it's incumbent upon the person collecting the data to be sensible about it. So if you're collecting a child's height, you probably want to measure the child's height at least once a year, and then you can kind of estimate how fast the child is growing between times. But if you're estimating the speed of a car, once a year is not going to cut it. You're going to want to estimate much more frequently for a car. So just, keep that in mind, and then the person measuring the data has to be responsible about that data collection. Okay. So this type of question gives you an outright formula and a time step and says estimate the distance between two time endpoints. So we start the thing with velocity is 0, and we go to velocity, from time is 0, velocity is 0, and we end up at time is 2, velocity is 4. So we can make ourselves our own little table. Haha, it's a TV table, get it? Okay, bad joke. And 1/2, when you square it, becomes 1/4. And 1 squared is 1. And 3/2 squared is 9/4. And then 2 squared is 4. Okay, and we can still, now we just do the same thing we did before with our table, and I'm going to do an overestimate and an underestimate. I would like you to do that. So the over, you go do it and pause the video and I'll do it. Okay, so my overestimate, I got 3.75, and my underestimate, I got 1.75. And because this is monotonically increasing, when you do the under and overestimate, it's the same as doing the right-hand side and the left-hand side estimates. So, for example, add up all these guys, and this only works because you've got equal steps on the left-hand side, which I'm not guaranteeing you in the exercises, but it often happens. And then we had to add up these guys. So what we ended up with was this overlapping set of values. So this often happens, and when that happens, you can save some time calculating by calculating that overlapping range and taking it from there. Okay, now the next question you're going to get is which estimate is better and why? And for this, I need to draw you a little picture. So here's what I want you to imagine. Here's my velocity graph, and I've gridded it up into 1 by 1 black squares, but I've subdivided into quarters. Those gray lines are subdividing the quarters so that you can see where that goes, okay? And so I want you to imagine what this, I want you to see the concavity in this graph, but I'm not connecting the dots because I don't want my diagram to be too complicated, but I'm going to just draw the curve and then erase it for you. So I want you to see that this graph is concave up. Okay, so this is what it's going to look like if we underestimate everything. We're going to make the boxes on the smaller end. And this is what it's going to look like if we overestimate what's going on. So the overestimate and the underestimate in your mind's eye, I hope that makes sense. Okay, so what's going to happen if we take an average these lines, which I'm going to call trapezoid. So here's what's happening. Like, think for just 1 second, like this region, if I filled it in with what's called a trapezoid, that would exactly be halfway between the overestimate, which is this guy, and the underestimate, which is this guy. So the trapezoid is exactly halfway between the over and underestimate, right? The actual right here, the actual is going to be under the trapezoid. So the actual is less than the trapezoid, which means that the underestimate is closer to the actual than the overestimate is. And this is because we are concave up. If we're concave down, we get the opposite argument. Okay, so since we're concave up, we compare against the trapezoid, and the trapezoid is an overestimate. Therefore, if you have to pick an over or underestimate, you go with the underestimate, which is closer to the actual value than the overestimate is. The trapezoid is still probably a better deal, okay? But you don't get the trapezoid. It's just for comparison purposes. It's a thought experiment, okay? Okay, now one of your questions is to ask for an over or underestimate for this kind of curve. It kind of looks like a bell curve of some sort. Hint, if you've taken statistics, you may have seen this guy before. And so I'm going to try to sort of make this work for you. Maybe it looks kind of like this. Okay, it's not perfect. Okay, so it's supposed to go on forever with an asymptote. Okay, so if I'm going from, let's say here's t equals 0, here's t equals 1, it's not exactly right, okay, but this is roughly, this is just to give you a visual on this. If you're going from -1 to 1 and you want to make 5 boxes, you're going to want to make, hold on a second. Okay, I'll let you figure this out, but I'm going to just erase this line in the middle so visually it'll make more sense. But if you're going to make 5 boxes, you need 4 dividing lines. So those are 4 boundaries. And so what you're going to do is you're going to make overestimates and underestimates. So if you're going to do an overestimate, you have to, in this case, go to the middle of the box because of the symmetry of the problem, because the max is in the middle. And then for the other boxes, you're going to overestimate them like that. And this is essentially what it's going to look like. So I wanted just to give you a visual on that. And then if you want to do 10 boxes, you know, you're still going to get 2 boxes like this that look the same, but then these 2 boxes are going to look different. So you're going to have an overestimate and an overestimate, and then an overestimate like this. And similarly on the other side, you're going to have an overestimate, an overestimate, an overestimate, an overestimate. But you notice that, for example, in this box, you're getting the overestimate from the left-hand endpoint, and from this box, you're getting the same box, but the overestimate is coming from the right-hand side. So just be careful. If I say overestimate or underestimate, make sure you hit the max and min in that box. Don't just do right hand, left hand thing, okay? Because this particular curve increases and then decreases. So I'm going to let you work out the arithmetic on that, but I wanted to give you the high level diagram for that. Okay, then the next one, this picture does not look exactly like the one in your worksheet, but I just wanted you to understand that in the worksheet, each box is a 1-by-1 box, as it's been, but it's an actual photograph. And Professor Robinson took this photograph and lined it up very, very carefully. So you have to look at the slope over a certain range. So in this case, I want you, this picture is different, but between each of the, you look at the horizontal axis and you break it off by however many times you have to get from the 0 to the 0. And then within each one, you say, aha, within this time interval, my slope is 4. And then within this time interval, my slope is 2. And then to the best of your ability, up to a half, you can do either integers or a half. Look at the slope for these guys and so forth. And you should find a symmetry. And I purposely made my diagram different, okay, here. But your diagram will be slightly different. But you're going to look at where the little node points are in the diagram and look very, very carefully, and you should be able to estimate the slope. Again, use integers, integer, or whatever 0.5. Okay, so it's going to be very, very close. He actually spent a long time lining that diagram up properly, so it wasn't an accident. Okay, and again, continuing with more bogus numbers, just to show you the process. The next part of the exercise says, using your table as if it were a table of velocities, compute the displacement of the water stream. Okay, so I'm sorry. What I meant was the x's should all have 0.5s in them. But that doesn't matter, because when you see 0.5, you know that this is the range from 0 to 1, and 1.5 means 1 to 2, 2.5 means 2 to 3. I want you to interpret all these little intervals as being ranges of numbers. Like, so the slope between 0 and 1, but you're going to write 0.5 as a representative of that range. Okay, but that doesn't matter. Okay, so the point is, how are you going to deal with this? Are you going to overestimate? Are you going to underestimate? You're going to do one or the other. If you over and underestimate, you should average them. And that's the same as using the trapezoid. So you can either make a trapezoid or you can do the average. And there is something magical that happens, because this shape that you're estimating should actually be a parabola. And a parabola is kind of magical in that if you do a trapezoid over this interval and it includes the vertex, your total accumulation is going to be okay. And I want you to think about why. I don't want to give away too much, but I want you to also look at the diagram. I want you to look at the diagram and what's going to happen. And this happens occasionally. When you do a numerical estimation of a calculus, once in a while you actually get a perfectly accurate result. And it feels like a fluke, but then when you look at the underlying math, usually it's not a fluke. Usually there's a reason for it. And so you're going to end up with a number, and then you're going to look at the picture. You're going to figure out from the picture, how do you know that the numerical answer you got is actually perfectly correct? That's what it's trying to say. Okay, and finally what you're going to do is you've got this picture of this water fountain picture. And this one, your water droplet starts its journey at 0. And it goes up and it goes back down. So this is like the max. So if you think about your little water droplet, starts here. Maybe I should make it blue. And then this little water droplet, actually, when it's going around like this, just in the y direction, it's just going up and down. Okay? That's all it does. So when you are asked about the total vertical distance, it's this vertex of this parabola, whatever this is, this distance times 2 is going to be your total. Okay, so that's how you know you're going to actually do your work. You're going to add up all your numbers, but actually in the end you're just going to compare it to how much distance there is from the zeros to the vertex, in the vertical direction. So this height here times 2 is going to be your answer. And question D is just to be very silly. That is not on it's not on the quiz, but Dr. Robinson put it in there, and so I left it in there because he was being silly, and I approve of silly. Okay, so I think that's all you need to know to get through that worksheet. I will see you in class.